Bhat from the Indian Institute of Science visiting us today. He received his PhD in electrical engineering from Stanford University in 1996. Then he worked at Motorola's Networking and Computing Systems Group under Advanced Products R&D Lab in Austin until 1999. He joined the Indian Institute of Science, Bangalore in 1999, where he's currently Professor and Chair, Center for Nanoscience and Engineering. His research is focused on nanoelectronics device technology, biosensors for point-of-care diagnostics, and gas sensors for pollution monitoring. He has 240 research publications in international journals and conferences, 10 US patents, and 14 pending patents. And he was instrumental in creating the National Nanofabrication Center at the university. And served as its chairman from 2010 to 15. He's a fellow of the Indian National Academy of Engineering. Many accomplishments, including the prestigious Dr. Abdul Kalam Technology Innovation National Fellowship in 2018, and Professor Rustam Choksi Award for Excellence in Engineering Research in 2017. He is a member of the Board of Governors of IEEE Electron Devices Society, and also chair of the Nanotechnology Technical Committee, and chief editor of IEEE TED Special Issue on 2D Materials for Electronic, Optoelectronic, and Sensors. And he's a founder and promoter of a startup company, Bhat Healthcare, which has developed first of its kind multi-analyte point-of-care diagnostic device for 5 blood tests and 3 urine tests related to multiple chronic diseases, including diabetes and its complications, anemia, malnutrition, kidney and liver diseases. And the company has received many recognitions. So, please.
Thanks a lot, Amit, for a very kind introduction. And firstly, I apologize. I would have preferred to stand there and speak to you. But because I don't have the remote slide changer, I'm forced to stay here and speak to you. So I'm sorry about that. Thank you, Thomas and Amit, for inviting me here. In fact, we have been talking to Thomas and Amit about possible opportunity for funding under Indo-US Science and Technology Forum. Part of the reason I'm here is also to discuss about that, and the proposal is due in August, and we hope that will come through. If it does, then I think that will open up possibilities for future collaborations, right? So what I plan to do is, give a quick introduction about this Center for Nanoscience and Engineering, and then specifically focus on 2 research threads in my group on gas sensors and biosensors, right? In fact, yesterday I was, I was talking to Amit, and I told him that there is a lot of similarities between Renew and what we are doing in this center. You started in 2015. I'm told we started planning for this way back in 2000, and we got our first funding in 2005, and we convinced the institute administration that this whole nanoscience and engineering should be anchored in a new center, right? And that is how in 2010, a new academic center was born in the institute. This is a new center which is a little different from what you have here, Renew, and that is we can also recruit students and faculty into this center directly, right? So, just 2015, the Prime Minister had visited to formally dedicate this center to the nation, right? So this is, starting from scratch, really. 2006 was a groundbreaking that we had for this center, and now 2011 is when we moved into this center. And what we have in this center is a national nanofabrication facility, which has been sort of benchmarked with the best university facilities in the world. And we also have a micro and nano characterization facility. And we have packaging lab, system engineering lab. As I will show you a little later, we start from materials and sort of go all the way towards systems. We cover the whole ecosystem. And we have a lot of thematic research laboratories such as NEMS, biosensors, photonics, and so on and so forth. Right? this is just a quick view of the 14,000 square feet clean room facility for nanofabrication, and we also have a very comprehensive 7,000 square feet semi-clean room for characterization, which has diversity of equipment, such as, for instance, it has material characterization, electrical, mechanical, and optical characterization, right? The whole suite of characterization that you can think about. Right? So at this time in our center, we are 12 plus 5 faculty, 17 faculty members. Large number of PhD students. We admit these students directly into the center. This is an interdisciplinary center. We have faculty from electronics, mechanical engineering, material science, physicists, a very diverse group of people who are faculty members of this center, right? And also our student intake is also very diverse. We get mechanical engineers, electronics engineers, physicists, material scientists, and so on and so forth, right? So it's a very, very unique center in that. We also have our own master's program, masters in nanoscience and engineering. And we have large number of technical staff who support our center because we have two major facilities, nanofab and characterization. We can't depend on PhD students to run the facilities, right? So we have technical staff who support and run these facilities, right? And in the last 5 years, we have from the center more than 500 publications. There's a lot of emphasis on translation. So there's a lot of patents that have come out and technologies and products coming out of the center, and also emphasis on startup, incubation and startup. And another unique thing that we are doing, it's kind of like what we had here in US, NNIN, National Nanofab, network. We build a network to create momentum and critical mass. We go out and train researchers, students from all over the country, bring them in and enable them to use the facilities. And now we are sort of opening up our center to also researchers from outside the country, right? So as I said, we cover the entire spectrum from science to systems, starting from fundamental discovery and really ensuring that we create societal impact by, creating some products, right? So some examples I'll give you. In the just last 5 years, some of the key products that have come out. This has been a very successful product, the MEMS pressure sensor for aerospace application in particular. The whole chain, starting from design of this pressure sensor, which is a piezoresistive bulk micro machine MEMS pressure sensor, and making a die, interfacing it with the electronics, packaging it, putting it in the right fixture, which has to go into the aerospace applications, such as, for example, helicopter or that is a light compact aircraft. The whole thing was done in this center, right? So we have the facilities to cover this entire spectrum, right? So now this product is fully qualified, and is actually flying in the helicopters, for instance, right? This is again another very interesting example, just to sort of illustrate the breadth and the depth of things that we do. This is a mobile lab on palm device. We believe that this is only such device. I will talk a little more about it because this came out of my research group. It can do 5 blood tests and 3 urine tests. Again, this was productized way back in 2016, and it has been deployed in various places around the country. Right? We also look at equipment for fabrication, right? This was a conscious decision that at the end of the day you should really cover the whole ecosystem, and we have a lot of material scientists in our group. They developed their own equipment, and we decided that we should also start commercializing these equipment, right? So this is, for instance, a graphene CVD reactor, which was again fully developed in our center, transferred to a startup company over there, and now this is the fully functional product, which is out there in the market. Right? So these are a few other examples of prototypes and products that have come out, again covering the whole range of applications. One very important thing that we have been doing is industry interaction. The Indian Institute of Science, where this center is located, is the oldest institute in the country, more than 100 years of history. In fact, a lot of IITs came out of this institute. It was essentially known only for research, So in fact, Amit was asking, has there been a change now? I mean, are you interacting with industry? So this was a very conscious decision that we took when we started this center, that industrial interaction is extremely important. We have a program called Industry Affiliate Membership Program, right? All these companies are current industry affiliate members. We work with them very closely. We define projects which are relevant to these companies and, get funding either from this company or various other funding opportunities. We have a very big focus on startups. In the last 5 years, we have created 4 startups out of this center. The focus is really to create deep science and technology based startups. In fact, we have just now received funding from the state government to create 25 startups in nanotechnology in the next 5 years, right? So that's a very, very big emphasis in translating the technologies and research. So these are the research focus areas in our center. I see that a lot of this connects to what you're doing at Renew, actually, right? So power electronics is one of the big thrust area, gallium nitride and gallium oxide based power electronics. Electronics beyond silicon based on oxides and chalcogenides, that is also a major emphasis. Photonics, for instance, plasmonics based sensors, devices, photonics for on-chip and long-haul communication, right? Silicon photonics most importantly. And healthcare is another very important area, energy and nanotechnology for agriculture, food and environment, right? So these are the thrust areas, and there is a new initiative that we have just begun. We call it 3D system scaling. As you know, people are talking about Moore's law coming to an end, right? Because device scaling has become extremely difficult. So the question is, how do we really increase the performance of systems in the future, right? And that is where we need heterogeneous system integration, right? So for instance, you want to not only have integration of memory and compute engines on your chip, but you want RF, you want sensor, actuator, and micro needles or what have you, everything integrated on a single chip, right? This is an emerging research area, and we have a major emphasis in this 3D system scaling as well. Okay, so with that very brief overview on the Center for Nanoscience and Engineering, let's switch the gear, come to the work that happens in my group, which is a Nano Devices and Sensors Lab. We look at 2 threads. One is looking at devices beyond silicon. So we look at, for instance, 2D material based devices or gallium nitride based devices. We also look at RF CMOS. There is a lot of activity on nanoferrites, integration of nanoferrites, for instance, to build a very high quality factor inductor for RF CMOS application. So this is one thread. The other thread is on sensors, right? So in that we work on 2 major areas. One is biosensors and the other one is gas sensors, right? So this is what we do in my research group. And today I'm only going to focus on metal oxide gas sensor to begin with, and towards the end of the talk, I will also touch upon biosensors that we have worked upon. Right. So, there are a lot of ways you can build gas sensors, either using a cantilever or using photonics. But we focus in my group on metal oxide gas sensors, right? It's a very simple device. It's a 2-terminal device with a metal oxide put on an insulating substrate. So the sensing happens, it's a chemi-resistive sensor. The resistance change in this 2-terminal device is essentially calibrated to the gas that is interacting with this 2-terminal device. So this is essentially based on oxidation reduction reactions, redox reactions. As an illustration, if you have a tin oxide, which is an N-type semiconductor, when it is exposed to ambient, oxygen absorbs on this, and that there is an electron transfer that takes place, and that results in resistance of this device. When exposed to a reducing gas, for instance, hydrogen or any reducing gas, there's again an electron transfer that takes place, and because of that, the barriers change and the resistance changes, right? And you're essentially going to look at the change in resistance and calibrate it against the concentration of the gas that you're looking at, right? The only catch here is that these redox reactions, rarely happen at room temperature. You also need, activation for this, and you need to build a microheater along with this metal oxide, right? So initially what we did was really to build a wafer scale technology for metal oxide gas sensors. In particular, our emphasis was to build a sensor array, going towards what is called an electronic nose, right? So now this is a wafer scale technology that we have sort of optimized and, is more or less, is ready for sort of technology transfer as a product. This one has 4 elements on a single chip. The chip is about the size of 400 micron by 400 micron, the die, right? The 4 elements that you can see, each element has different metal oxide functionalized, which has specificity to a particular gas, as I will show you in a minute, right? So this is a very elaborate 8 mask process, bulk micro machining process, because you really need to create a microheater which has low thermal mass, right? So that is where you need to really etch out silicon, otherwise your power requirement will be very high to heat the microheater, right? So, with this you can have these 4 elements with 4 microheater. Each microheater can be heated to a different temperature. And when you talk of wafer scale technology, you also need to worry about yield. So we did a lot of work on this. And it turns out that you have to use a PECVD oxide as opposed to thermal oxide as a membrane, as an insulating membrane on which you want to put the metal oxide, a thin 1 micron PECVD oxide, because PECVD oxide has very high tensile strength compared to thermal oxide, right? You will have very high yields, otherwise the thermal oxide will just break down, right? The membranes will not be very, very solid, right? And we have used optimized metal oxides. Microstructure has been optimized. This, for instance, is a zinc oxide used for carbon monoxide sensor. The 4 element sensor that we did is for environmental pollution monitoring. Our interest was to look at carbon monoxide, carbon dioxide, sulfur dioxide, and NO2, right? These are 4 very important pollutants, right, in the ambient, right? So, there's a lot of optimization that goes on, and what is shown here, you will see a lot of these graphs later on. The way you calibrate the sensor is that, after you make the device, you have a gas calibration setup wherein you have a synthetic air flowing, right? And then you introduce the target gas. For instance, in this case, carbon monoxide. You have MFCs to control the concentration of the gas, right? So every time you introduce the gas, there is a change in resistance, and that is what is shown. And again, you remove the gas back, right? So the resistance goes back to its baseline, and as you start increasing the concentration of the gas, you can see that the response is increasing, right? These are the typical gas calibration curves, right? So, and this is, for instance, carbon dioxide, where you have to use, this is very important, right? For each gas, you need to use the right metal oxide, right? For carbon dioxide, for instance, we use what is called a distributed p-n junction, using a composite barium titanate and copper oxide. Barium titanate is an N-type oxide and copper oxide is a P-type oxide, right? We also dope it with silver to enhance the sensitivity, right? And this is tungsten oxide used for NO2 sensor, and vanadium oxide used for SO2 sensor, right? What we see is that we get extremely good repeatable response going down to sub ppm levels, which is what is required in certain gases such as SO2 and NO2, for example, right? What is very important to do is also to look at cross sensitivity, and that is another advantage of 4 element sensor, because you see these are metal oxide. You can't have, it's not like a gas chromatography that each gas has a signature, right? The redox reactions can happen due to multiple gases, although the magnitude of change in resistance could be different, right? And what you see here, for instance, is that you have response for this CO sensor and CO2 sensor, and you see that the particular metal oxide has substantial response to that gas, but it also responds to other gases as well, non-zero response, right? But once you have this kind of a calibration curve, you can have an intelligent electronics which should be able to take care of all of these signals and look at the composite signal and be able to let you know what is the concentration of each of these individual gases, right? So what we have done subsequently is to really miniaturize this sensor further, right? To go from micro to nano, right? So what we have done, there are two important things that we have done in this work. That is, firstly, we have gone from what is called a bulk micromachining process to a surface micromachining process. Because bulk micromachining process is not CMOS compatible. Surface micromachining is CMOS compatible. So in other words, you can make a CMOS chip and on top of it you can put these gas sensors, right? So this is based on surface micromachining, and the other important thing is, unlike the previous gas sensor array which was 500 by 500 micron, this gas sensor array is only about 10 by 10 micron. Each of the sensing element is just about a 1 micron by 2 micron. The heater, we call it a nano heater. It's essentially a 100 nanometer beam, which is designed appropriately, which is suspended so that it requires extremely low power for heating, right? And it's actually a bus bar structure. What you have is a heater going in the X direction and the sensing element going in the Y direction. And using this, it's like a memory array, you can think about that, right? Word line and bit lines crisscrossing, and here heater line and sensor lines are crisscrossing, right? So this is an interesting idea that we sort of implemented, and this is how each of the sensor looks, right? There is a micro heater and there is a sensing electrode with an oxide, appropriate oxide functionalized on top of it, right? So, this is how your the entire sensor array looks. There are 4 sensing elements here. I'm sorry, I don't have a pointer here, but what you see in the left bottom is essentially the entire sensor array, right? And the middle bottom is essentially the IR camera image, which shows that when you actually heat it, the heaters are heating, okay? And they are consuming extremely low power now. Earlier it was more than 20 milliwatts, I'm sorry, now it is less than 5 milliwatts, right? So again, we have done the gas sensing characterization, similar characterization curves that I showed you earlier. And the advantage from micro to nano, as you can see, heater power is substantially lower, sensitivity is enhanced compared to a micro gas sensor, and response is also much better, right? So going forward, we would like to really build a larger number of array of sensors, functionalized with different kinds of oxide and also similar oxide to build in some redundancy, right? You can do lots of very interesting things once you have a very small footprint device, right? So this is one direction that we are working on. The other direction, when we started looking at this nano sensor, is to ask the question, can we start looking at different kinds of nanostructuring, right? To be able to enhance the sensitivity and really come up with a very novel way of making this nano sensor, right? So in that direction, one thread that we are pursuing is what we call a chemically gated transistor, right? It's a suspended core shell structure. As you can see there, there is a metal core and semiconductor shell surrounds this core. This is extremely important because it creates some Schottky junction, right? Metal semiconductor junction, and there is a built-in electric field there. And it turns out this is extremely important because you can really build a sensor which is this electric field activated as opposed to thermally activated, and thereby sort of eliminate the microheater completely, right? So, and it's essentially again a 2-terminal device, and when you expose it to a certain gas, it essentially there's a redox reaction and there's a change in resistance. But what is also very important here is that this has to be suspended. I'll come to that reason in a minute. So this is how it looks on a silicon wafer. You have a thermally grown oxide, and you have built this core shell structure. In the middle of this core shell structure, this entire structure is suspended, right? And the way to do that, again we follow a series of process steps. This is essentially a fabrication process step. You have to deposit films, and what we do here to produce core shell structure is that we create a platinum beam. This is platinum oxide core shell structure, and that platinum beam, which is on silicon oxide, as I told you, should be released because I want it to be suspended, And that is why in the middle of the platinum beam, as you can see on the right top cartoon that I have shown, there is a constriction. The idea of constriction is that is where I am going to have a isotropic dry etching to be able to suspend that beam, right? Only in the middle, okay? And what I also do, typically you can do a isotropic etching using CF4 chemistry, but I also add oxygen. This has to be optimized appropriately so that it is in situ beam release and oxidation, okay? While I am releasing this platinum beam, because of the underlying silicon oxide isotropic etch, the fact that you have oxygen in your etching species, it also oxidizes that beam, right? And hence when you are done with the structural release, you get a core shell suspended structure, right? So what is shown here is just in the middle of the beam, right? We start with different thickness of beam, 10 nanometer platinum thickness, 20 nanometer platinum thickness, 30 nanometer platinum thickness. One thing that you notice is that after releasing and etching, the thickness of that beam in the middle increases, right? The 10 nanometer beam becomes 20 nanometer thick, 20 becomes 30, and 30 becomes 40, very consistently. And this is because when platinum is oxidized into platinum oxide, there is a volume expansion, right? If you look at the density of platinum oxide and platinum and do this math, there is 1:2, almost 1:2, the volume expansion, and that is why the beam in the middle expands, right? And also what happens is that we have seen that when we do this, if you start with 10 nanometer platinum beam, the entire platinum gets oxidized, right? So there is no core shell structure, okay? Because this oxidation that happens, we have seen that from top and bottom you oxidize about 5 nanometer platinum, right? And the 10 nanometer is a completely oxidized beam, whereas 20 and 30 have a core shell structure. And this is very important, and this is what I told you, that there is a beam expansion from initial thickness of platinum into a core shell structure, but 10 nanometer beam does not have any core, it's completely oxidized platinum oxide, right? This is very important actually. When you do Kelvin probe microscopy, you see that if you suspend the beam, right, what you plot there is contact potential, and from contact potential you can infer what is the work function. There are two cases, right? One on the right is a beam which is not suspended. Okay, so when you do the line scan, Kelvin probe microscopy, your contact potential is identical. But when you do this on the left side, where only the middle portion is suspended, you see that there is this change in the work function in the suspended region, and this is very important. And this will eventually help you to do the room temperature sensing, right? Only in the core shell structures which are suspended, we see a room temperature, sensing, right? And we have done the XPS and TEM analysis to sort of, show that there is a core shell structure, but if it is just a 10 nanometer beam, then the entire thing is oxide. There is no platinum core, right? And as I told you, on the left top, you see that at room temperature, only 20 nanometer and 30 nanometer starting platinum thickness beams show sensing, whereas 10 nanometer does not, right? On the other hand, if you heat it, remember I told you, when you heat it, there is this thermal activation and redox reactions take place, right? When you heat it, even the 10 nanometer responds, and in fact 10 nanometer is better than the rest, that is expected because in 10 nanometer, the whole thing is oxide. So the redox reaction happened throughout the thickness of this beam, suspended beam. Whereas in a core shell structure, there is a little bit metal inside which doesn't contribute. It's like a DC offset that I have, right? So the sensitivity at high temperature, 10 nanometer gives you best. But if you want the room temperature sensing, you really have to go with the core shell structure, right? And these sensors have extremely good response and recovery time, and the power dissipation is amazingly low, right? Microwatt kind of power dissipation, because in a core shell structure you don't really need heating for the sensing to happen, right? just some benchmarking, the devices that we have been able to make show extremely good limit of detection. On the x-axis what you have is limit of detection, what is the lowest that you can detect. On the y-axis the sensitivity of this sensor at a given concentration of the gas, right? Okay, so now we have been sort of building on this thread to create this core shell structure. We are asking the question, what else can we do to create the core shell structure, to be able to come up with a whole range of, a menu of processes, for instance, right, to be able to create this core shell structure. So one other interesting thing that we have done in the recent past is to use a joule heating, right? So this can be done anytime, it's like sensor on demand, right? So what we do is we create a suspended platinum beam. So while we suspend this, it's only a CF4 chemistry, so there is no oxygen use. So it's essentially a platinum beam which is suspended. If you have a suspended platinum beam, if you apply voltage, x-axis, there are two curves that I'm showing, right? The black curve, which is B, is unreleased beam. What it's showing you is that eventually when you start going to higher and higher voltage, the joule heating will essentially burn this beam. Okay? If it is suspended, there is very little thermal mass, and you will start burning this beam much earlier, right? And that is what is illustrated here, right? So we said, look, this is what happens typically when you apply voltage in the ambient. Why don't we, start doing an experiment, flow oxygen instead of ambient, right? So this is all fabricated suspended platinum beam, flow oxygen and then apply potential, right? So now the beam is heating and there is oxygen in the ambient, you should be able to oxidize, right? And if you oxidize, it should not break, right? Because it should be a self-limiting process. Once you start oxidizing, the resistance should start increasing, current should decrease, and you should be able to get a core shell structure only in the middle. So that was the idea, and indeed you get a very nice structure, and this is what is shown there. This happens only if you do it in the oxygen ambient, right? So as you can see in the middle of the beam, right, it's not bright, right? It's showing that there is a change in material, right? Platinum has been oxidized there, right? And you can control the potentials, voltages, and currents, and you can really have a very good control in forming a core shell structure. This is post fabrication, you can do it anytime, anywhere, right? So that is the beauty of this process, right? And it does give you excellent sensing performance and repeatable sensing performance as is illustrated here, right? And then we said, okay, let's start building an array of these sensors, right? So what we do is essentially we create an array of suspended platinum beams, and again expose it to oxygen ambient and apply the appropriate potential, and you get array of suspended core shell structures as is illustrated here, right? And the array gives you extremely good sensing performance compared to single gas sensor, suspended gas sensor, right? You can also do plasma oxidation, right? You create a suspended structure, expose it to oxygen plasma, right? And then you can build it. And we have now gone beyond platinum oxide. We are doing it for tungsten oxide in this case. We are looking at other metal combinations as well, right? So this, for instance, we have used for hydrogen sulfide sensing, right? And this is the sensing performance for hydrogen sulfide. Again, a core shell, tungsten oxide beam here. Right? And in gas sensing, the key is really, surface reaction. So if you give more surface for this reaction, your sensitivity will enhance, right? So we have been looking at how do we do some post-processing for these suspended structure, create some more nanostructuring on top, so that you have more surface area and be able to get much higher sensitivity. So this is a work that we published recently on polystyrene bead, nanostructuring without the use of lithography, right? So we use this as a template to do our deposition of metal oxide, right? So when you do the deposition of metal oxide through these templates, you get a very nice honeycomb structures, right? Honeycomb zinc oxide rather than a planar zinc oxide which we were doing earlier, right? So this is a platform. You can use it for any other metal oxide as well, right? You can do it for vanadium oxide or various other oxide, right? The fact that you have this kind of a nanostructuring, there is so much surface area for reaction, right? And that in turn gives you substantially better sensitivity. And as is shown here, compared to a planar film, all other nanostructured film give you extremely good sensing. Again, this is for carbon monoxide sensing with zinc oxide, right? Varying concentration of the gas, and selectivity in presence of other gases as well. Right? So as I told you, we would really like to not just build sensors, but really see how these sensors can be used in a real application, right? So this is a project we have been working for last couple of years actually. We have created a system we call it EnviroBat. We have designed it to look like a bat. This is essentially for environment pollution monitoring. The idea that we have is that this should be, especially in India, I don't know how it is here, this is much better here, but our cities are really polluted, right? So the idea is that, we should be able to have this kind of a IoT system in every traffic intersection of a city, right? That you can do only through this low-cost metal oxide sensing technology. You can't do it with the gas chromatograph kind of a system, right? So for instance, this system has not only the gas sensors that we have developed, it also has humidity, temperature, particulate matter and so on and so forth. And we have started sort of deploying this in the field, to collect the data and, this is where we start interacting with, that is one very nice thing that I saw in Renew. I mean, we are interdisciplinary, but you are more interdisciplinary than us, right? You also have people here who are civil engineers, environment specialists, I guess lawyers and so on and so forth. But here we start, interacting with our other colleagues in other departments, who are environmental specialists and, they use this and we work with them to really sort of collect this data over several days. And now we have actually built a system, wherein you have a very nice GUI, you can deploy many such devices. You can probe this device through a Google map, for instance, right? You can go to a very specific device, deployed in a very specific location in the city, and sort of collect all the pollutant data, in the central server, right? So this is a very, very important project that we have. We hope that in the next 2 years, we should be able to do a lot of work in this, collect a lot of data. One of the biggest problems that we are encountering right now is how do you recalibrate the sensors? That is one issue in these low-cost sensors, that once in 6 months or so you need to recalibrate, right? So we are looking at various methodologies and algorithms to recalibrate these sensors, right? And we have also used this in indoor setting. When you have a big conference, there are a lot of people inside, so we monitor the carbon dioxide level, and when the hall becomes empty, the carbon dioxide level goes down, and so you can use this for a lot of very interesting applications, right? So that is the eventual goal here. Okay. So before I switch the gear, any questions on this?
Yeah. So what is you said there's low cost sensors. What are we talking about in terms of cost?
Well, the cost is a funny thing, because I know that because this I have productized, and it depends on the volume, right? But when I say low cost, the die should be less than $1. That is my low cost, right?
So the whole sensor, array that you have.
Yeah.
For the EnviroBat, for example.
Yes.
What would that whole system sell for?
Oh, including the electronics and all that.
Right.
Well, that should be, I would say less than $50. That is the target that we have.
And you said it has to be recalibrated every 6 months. Why?
Okay. One of the things that we see in metal oxide is that they drift. See, these are chemi-resistive sensors. If the baseline resistance drift over time, the way we have calibration done is we have baseline resistance and resistance when exposed to, let's say, 1 ppm gas. That delta is what we are relying on.
Right.
If your baseline shifts, that delta needs to be recalibrated.
By heating the sensor? heating the metal oxide? Or
No, you just need to know what is the new baseline.
Oh, you just need to, I see.
Yes.
I see.
It's as simple as that, right? So one way is that either you take the sensor out, because now sensor is exposed to ambient, right? If you want to know what is the new baseline, you need to have a controlled ambient, right?
But in that case,
Or you need to take a more expensive, let's say optical sensor. You measure the gas in the same location. This could be a mobile sensor. And then, based on this, you recalibrate your algorithm there on the electronics. Yeah, you had a question.
yeah, but in that case, when you do the selectivity, you said you are using electronics. You
Yeah.
are not really using the material, like a sensing material.
The material
For
gives
the
you
selectivity.
fairly good selectivity to begin with. I showed you that, right?
But
There is.
yeah, but at the same time, like in the environment, you can have carbon monoxide, carbon dioxide. You can have everything, anything can be used there, right? But for different material, it's most sensitive to one kind of material,
Correct.
Gas,
Correct.
or maybe to others as well. So how you really see I do the selectivity.
Right.
Sensitivity part of
Right.
course. It's
So
all
there are two things that we need to do. Firstly, we need to know what are the typical gases in the ambient. So it is application specific, right?
Okay, you have-
That is already very well calibrated. Based on these, we have these big mobile gas stations, right? They're very expensive, right? Few $1,000s, right?
Mhm.
So based on that, you know that these are the 4 most important pollutant gases. All other gases, you can just ignore that because very little. The pollution is because of the vehicles and what have you, and that is very well known, right? So to begin with, the field utility and the constraints that you need to work with, and then once you make the sensor, we have already chosen the material which give you fairly robust cross sensitivity performance. There is very small residual cross sensitivity which can also be corrected subsequently, right? So it's a 3-step process.
Okay. Thank you.
After
Yeah.
Yeah, just is there any possibility to over time to the metal you use over time it lost its oxidizing power, that is reducing power over time is metal.
Metal oxide.
The metal oxide.
Metal
is
oxide,
there-
yeah.
there-
Yeah. See what we have seen in these metal oxide sensors, the redox reactions are fairly reversible, but for instance, we have done this experiment for almost a year, right? At least over a year, we still see the redox reactions happening, right? The only thing that we have seen is a baseline drift, right? That needs to be corrected.
So over time we can see the redox is decreasing, then you to adjust your baseline for calibrate the sensor again.
The baseline resistance itself
Yeah,
drifts.
yeah.
Yeah. We need to know what is that baseline resistance and
Okay.
Recalibrate.
And another thing, is there any way to develop this kind of sensor for PM 2.5 monitoring, something like that?
so far we have not looked at particulate matter sensors, but maybe not using metal oxide, but we should be able to look at it. Right. We have thought about couple of ideas, but we have not yet started anything on that.
There is a lot of sensor already in the market.
There are already a lot of sensors in the
But it's
market.
not a stable reading, it's highly sensitive to other particle, and reading is sometimes you get a very weird reading.
Yeah. Right.
And another thing, is it possible to bring this kind of sensor in the cell phone?
That is the eventual goal, right? The holy grail is really to do that, right? Because with my cell phone, I should be able to figure out what kind of air I'm breathing, right?
Yeah, it's
So-
good for personal health implication, because
Yes.
if you know the health outcome.
Correct.
Because people are bringing some of the things, Samsung,
Yeah.
they invest a lot of money to monitor people's health outcome.
Yes.
Related to their pollution.
Correct.
If you simultaneously monitoring the personal pollutant, then
Yes.
it will be good for the epidemiological study. For
I completely agree with you. I think that is what we should aim for.
So you need to miniaturize your sensors even more.
No, I think this miniaturization itself will work actually.
I see.
Yeah.
Right. So I think we should be able to do that. I think the only thing is the reliability.
Yes.
Right. How long it will work, 1 year, 2 year recalibration. If we can figure this out, I think that would be.
I have a quick comment. These were zinc oxide based, right? Some of the
No, the zinc oxide is for carbon monoxide.
Oh, only carbon monoxide.
Yes, not all is zinc oxide
Right, so
because
there's an array of them.
yes. Tungsten oxide,
Because
you
you
know.
could use for increased sensitivity. If you're already getting better sensitivity than most other sensors out there, as you showed in one slide.
Yeah.
If you were to create one-dimensional nanorods of all these metal oxides, which you could easily do, I think.
Yeah.
1D nanorods or 3D
Yeah.
nanorods, right?
Right.
Then your sensitivity may go up by an order of magnitude.
Yes.
So you still have room to play.
Yes,
I
certainly. Right. And doing that array is very good, not only to have different elements, but also redundancy, right? So you can get signals from multiple elements and, that would be a great thing. Yeah.
Tarun Singh from Mechanical Engineering. I'm sorry you came in late. So my questions might be redundant because you might have already answered this. What is the footprint or the size of this? I'm thinking, could
Yeah.
this be on a mobile sensor, on a mobile platform?
Yeah. A good point. We discussed that. There are two versions that we had done. One which we call a micro gas sensors, where the footprint is 500 micron by 500 micron.
Oh.
4 elements for CO, CO2, NO2 and SO2. And we have a next version which is only about 10 by 10 micron.
So you do NO, NO2?
NO2 right now. NO2, SO2,
Okay.
CO, CO2.
Can you do NO?
We can, but not right now, right? I mean, this one we have not done, but we can do that.
Because I'm thinking that for the auto industry, that would be of tremendous interest.
Yeah.
Because,
Yeah.
NOx emission is critical for
Yes.
the auto industry, and
Yeah,
if you do NO, NO2.
Right. We were driven by the specifications that we had for environmental pollution, and it turned out the NO2 was more important in this application. But NO should be possible. I don't see a problem. Yeah.
And this, sorry, when I came in, you were talking about drift in the sensor. Right?
Yes.
Do you have a clear understanding of what causes it? Meaning, or rather, if you can develop a model, then we can do Kalman filtering, and then you can estimate the drifts on the fly.
Yeah, you are absolutely right. So we do know why the drift happens, because this is a metal oxide, right? If you are heating this metal oxide, it's like annealing the metal oxide. Over time the metal oxide structure is changing slowly, not immediately. So because of that, there is a constant increase or decrease in the resistance. And as you quite rightly said, if we can have an algorithm, how much heat is it exposed to, at what temperature and how long,
And that
we
is-
should be able to build an algorithm.
Yeah.
for that. Yes. Eventually that should be the way to go.
Yeah, then it's completely
Yes.
autonomous.
Yes.
Yeah.
Yeah. The only other thing that complicates the matter a little bit is that this drift turns out also not only governed by the heater temperature that you try to set in, but the ambient humidity and ambient temperature. Right. So you need those variables as well to be able to, do this complete modeling.
So
And that is the reason we have put the humidity and temperature sensor there.
Yeah, then you can automatically calibrate your
Correct.
sensor.
So we should probably move on. Yeah.
Well, just quickly.
One more quick question
Yeah.
before.
Yeah.
You said the suspended platinum wire, platinum oxide, has
Yes.
a different work function.
Yes.
I don't understand because it's a surface phenomenon, right? So it shouldn't depend on the bulk.
Very good point, and we have tried to look up a lot of literature on this, and what we have found out, maybe this is where some fundamental work can be done, is that when you really scale it to that dimension of 10 nanometer, the work function also depends on the environment.
Okay.
What kind of environment is around this it's not bulk anymore,
Okay.
right? So whether the environment is sitting on an oxide or it's air, that influences the work.
This is totally unexpected actually.
Yeah.
Because we assume that work function is
Exactly.
controlled by the surface
Yeah,
performance, right?
Yeah. This happens only when it is extremely
Okay.
thin,
Very good.
very thin. And we have done it so many KPFM measurements, every time very nice curves showing this dip and
Totally unexpected.
Yeah, exactly. So let me quickly change the gear and give a very brief 10-minute on this electrochemical biosensors. I can spend an hour on this, but when we started this research more than 10 years ago, we wanted to really come up with a new paradigm in the context of diabetes, but we have gone beyond that. And it was very clear that glucometers have become part and parcel of a diabetic patient today. And there are so many glucometers also out there, dime a dozen glucometers. But the problem, if you talk to endocrinologists, is that the glucose measurement is not sufficient to manage diabetes. Okay, and so we need to really go beyond this, right?
So when you say sufficient, you mean calibration accuracy?
No. I'll come to that in a minute, right? In fact, some endocrinologists that I've talked to, they say that glucose measurement is like a random number generation. Depending on when you measure the glucose, during the day, fasting, postprandial, you get different values, right? So for doctors to see whether the treatment modality is working or not, they need some averaging. Okay, so they want A1C, for example, which gives 3 months average. Now ADA, American Diabetes Association, A1C is a gold standard for diabetes. Not just managing, even for detection, they say A1C must be measured, right? So because there are a lot of studies which have clearly indicated that A1C concentration, typically it should be less than 6. Of course, that is also a moving target. Recently, ADA said it can be up to 7%. The fraction of hemoglobin molecules which have been glycated, right? That is what it is, right? So when it increases linearly, the complications such as diabetic nephropathy, retinopathy, they increase exponentially. So that is why you need to control A1C, right? So, A1C has to be done, right? There are very few solutions for, point of care A1C measurement, right? But we said, let's also go beyond that. There's a new kid on the block, which is called glycated albumin. In fact, even PATH labs don't do it, don't measure it. The pioneering work on glycated albumin has happened in Japan, actually. Albumin, just like hemoglobin, is a protein. Any protein in the body goes through this process of glycation. Glycation is a process where when protein is exposed to glucose, there is this, binding of glucose and this protein. This is an irreversible process, right? So albumin, when it goes through glycation, you can measure glycated albumin. If you do that, it gives 2 weeks average blood sugar. The reason is half-life of albumin is 2 weeks as opposed to hemoglobin, which is 3 months, right? So it's as simple as that, right? Because it's reversible, if you can measure the fraction of albumin which is glycated, you get 2 weeks average, right? So, and in certain cases, such as certain hemoglobinopathies, such as sickle cell anemia, for example, HbA1c does not give you what is the glycemic condition, okay? Whereas glycated albumin can, right? And in gestational diabetes also, right? You can't wait for 3 months to figure out how severe the diabetes is. You need to really get a value in 2 weeks, right? So we said, let's see whether we can build all these point of care, right? So that was the boundary condition that we sort of set in. So we said, okay, really we should build a platform, right? So that going forward, we should be able to add more tests to this platform. As of now, these are the tests which are available on this platform, right? And we hope that going forward, we should be able to add more and more tests onto this platform, right? So again, when we started looking at it, right, there is a very important difference between biosensors and autoanalyzer. If you look at IUPAC definition, right, biosensor is a self-contained integrated receptor transducer device, right? So there is a receptor and there is a transducer. In comes a biosample, could be saliva, urine or blood or what have you. You should generate a signal which should tell you what is the concentration of a biomolecule, right? But important thing is accuracy and efficiency, right? So you need to have specificity because there are sea of biomolecules in the biofluid. You need to have the right receptor so that the receptor is sensitive to a particular biomolecule, right? And once you have that, you need to produce a signal, right? And that signal's transduction is also important. When we looked at the literature, there are a lot of receptors which have been looked at. Enzymes and antibodies are the most common, okay? And in fact, they are great. In PATH labs, for example, immunoassays are very standard. They use antibodies and enzymes. But the problem is, antibodies and enzymes are biomolecules, they are very finicky. They are not good for point of care. point of care should be, operatable at very wide range of humidity and temperature, right? So we consciously decided we do not want to use enzymes and antibody, right? So we've essentially focused on specific ligands and metal ions and some specific chemical receptors. And in terms of the transduction, again, there are a lot of possibilities, right? Our focus was essentially electrochemical, right? Simply because, electrochemical is again, we have been working on redox reaction on metal oxide sensors also. Electrochemistry is also redox, right? And we have glucose sensors out there which are, the most successful, deployment of electrochemical sensors, right? So that is what we said. And, just a quick primer on electrochemical biosensor, Professor Clark is the father of biosensor, if you will. This electrochemical strip essentially has 3 electrodes, right? They're called counter electrode, working and reference electrode, right? And, you apply certain potential with respect to reference, and you have a current flowing through counter and working because of the redox reactions taking place at the working, right? The working electrode is appropriately functionalized. That is the key. For instance, in glucose sensors which are out there today, glucose oxidase is an enzyme that is used to give the specificity, which oxidizes glucose into gluconic acid. You typically use a ferricyanide as a mediator, and you apply the appropriate working electrode potential. You can essentially look at the redox reaction, and you can either do what is called a cyclic voltammetry or amperometry, and based on the calibration curve that you will have, current versus the concentration, what is the concentration of the analyte, right? Looks fine, right? But if you look at the biosensors market, point of care, as of 2015 or so, it was more than $15 billion, right, worldwide. However, the hard reality was that more than $10 billion was glucose sensors. It was only glucose and glucose, right? So there is really a big challenge that, why don't we have good biosensor going beyond, right? Again, the problem partly, I think, is also coming up with the right receptor, right? So I'll give just one example, right? Albumin sensors that we have worked on, serum albumin sensor, right? We also can do urine albumin, right? We call these sensors that we developed as physiology-inspired sensor. I'll come to that in a minute. The problem with albumin sensing, albumin is a protein. Unlike hemoglobin, which is a metalloprotein, there is a heme center, iron center, which is amenable for redox reaction. Albumin does not have an active redox center, right? It's a 585 amino acids, and from that perspective, it's like an insulator, right? So I need to have a current from this biomolecule. So there is no way I can get a current out of this biomolecule, right? So that is why we do not have very good albumin sensors out there, right? In path lab, of course, you have various other techniques to do the measurement. Firstly, it's done using serum. You need to separate serum from the whole blood. That is why when you go to path lab, it's called serum albumin test, right? Whereas what we do is a whole blood albumin test. We don't even do any processing, right? So then we started looking at studying this albumin molecule a little more detail. And it turns out albumin is called a molecular taxi in the human body. Albumin is synthesized in liver, then released into bloodstream, and it has a 2 weeks lifespan, as I already told you, in the context of glycated albumin in the bloodstream, and then it is disintegrated, and if your kidneys are working fine, no albumin should leak into urine, right? If a small quantity of albumin leaks into urine, that's called microalbuminuria, right? A micro quantity of albumin in urine, which is an early diagnosis for kidney disease, right?
It is one kind of nephrology.
Yes.
Yes.
Yeah.
Just the initial state,
Correct.
first sign of nephrology.
Exactly. Yeah. So then we asked the question, what is albumin doing for 2 weeks in the human body, right? It binds to a very large number of substances, fatty acid, metal ions, hemin, bilirubin, lots of pharmaceutical drugs that we take. They first bind to albumin, right? So we thought, can we make use of this property, right? And somehow develop a robust sensor for albumin, right? And then we figured out that copper and hemin have very high binding constant. In fact, copper has an association constant with albumin which is 10 power 16 per mole, one of the highest actually, okay? So, we said, okay, let's think about an experiment, okay, This was a hypothesis that we had. Albumin binds copper, and copper is redox active, right? Copper 1, copper 2, very good redox active, right? So let's create a strip just like a glucose strip, right? But instead of glucose oxidase, we need to put copper salt, right? And of course, a lot of devil is in the detail. You need to have the right pH of this, and also when you do the amperometry, you need to have the right wait time, because otherwise copper can also start binding to other stuff in the blood, right? But if you can do that, if I can somehow functionalize this chemistry, copper salt, with the membrane on top of my electrode, and then put my blood on top of it, right? Albumin should bind to copper. I do a copper redox chemistry. Whatever is bound to albumin, I should not be able to detect, because copper is very light. Albumin bound to copper is extremely heavy. Redox reactions are all diffusion controlled. Okay, so if all that is fine, I should get a current which is an inverse function of albumin concentration. This was an hypothesis. Okay, when you start with an hypothesis, then you do a lot of experiments. First you make sure that binding of copper happens with the HSA. We did a lot of UV analysis, and there are two binding sites, the N-terminus binding site, and there are also multiple binding sites. And after that, you also figure out what should be the right concentration of the copper to be used on top of your membrane on the functionalization. And then you don't go to the blood. You first do this on a simple buffer such as sodium chloride buffer, which is a support electrolyte for your electrochemistry. And you don't even go to albumin in the blood. You just buy sigma albumin and do a lot of experiments, optimize all this chemistry, right? And then go to plasma before going to whole blood, right? Because albumin is a plasma protein, unlike hemoglobin, which is in erythrocytes, right? And once you establish in plasma, then you go to whole blood, right? So this was a very, very elaborate, very interesting process, which took about 2 years and thousands of samples, real blood samples, right? And and then we got an excellent correlation between our technique on strips compared to the gold standard of doing the albumin measurement. And then of course a lot of for clinical acceptance you really need to do a lot of tests, and we were able to do a similar development on other receptors for other biomolecules as well. And then it took us this development of coming up with the right receptors and sensing validation took us actually 2 generations of PhD students, right? It's about 7-8 years. Then fast forward 2 years of product development. Now we have this product, which is what we call a multi-analyte diagnostic device, point-of-care diagnostic device, which not only does diabetes management but also does anemia and malnutrition, kidney disease, liver disease. These are the current tests that are being offered, and this is currently this is for clinicians. Right now we are also working on another version for home diagnostics, right? And this has been used very successfully, and the product has received lot of recognitions as well in India and also outside, right? So this has been a very interesting journey for me, at least, taking from lab to land, right? Not just publishing and patenting, but really coming up with a product which sort of makes an impact in the society, right? So that's it, and thank you very much for your attention. That is the bird's eye view of our center from the drone. This was taken from a drone, right?
So how far are you developing blood creatinine sensor?
We already have a urine creatinine, which is in the market. Blood, we are working on it, right?
Yeah, it will be a breakthrough, because all of the dialysis patients, they need to monitor the creatine three times a week.
Yes.
So again, what is the price of this unit?
The price of this handheld device is, I'm trying to convert it into US dollars. Right? In Indian rupees, it's 50,000 rupees, which would be, let's see,
$100.
So it's about $800.
Yeah, 800.
less than $800. Yes.
And
yes.
its life is?
Well, we have been, in the field. It's operating for 2 years. It's still working fine. Right.
We should start a company here in Western New York. Okay, if you've got something
We are
that
actually now-
works,
we are-
it'll sell. I mean, people will buy it. I mean, individuals will buy it.
We are
It
now-
actually works with just a blood drop.
Yes.
And we just had a big failure of a company called Theranos.
I know. We have been following it for last 10 years.
Oh, you've been working with them?
No, we have been following with what they are doing, right? So
let me
what we
see
are doing
what-
is completely different.
Why does
That's a
copper-
big,
So you use copper, salts and all that here, right?
only for albumin, yes.
For albumin.
Yeah.
But for albumin you said copper. Why copper? You said there was a
Very high binding of copper with
Why?
albumin.
Why?
Well, why does copper bind? I think that's very well established, Thomas, do you know why? Right? We are sort of
constant.
making, huh?
No, but that's
Bind.
that's where I was going with this.
The energetic more favorable.
So
You've
which
got,
part
you've
of-
got a periodic table.
Uh,
If you find
Eh, eh.
copper has a high
For
sensitivity,
this particular
right,
album.
then I can go to the next thing in the periodic table, which will also be good. So that's why I'm asking why
Okay,
copper.
no,
Right.
there's a lot of study that has been published. Several metals bind to albumin. They've also investigated the binding constant of different metals. Copper has the highest binding association constant. Why? I don't know.
Actually, it might be the terminal end
It's
of
a
the-
biochemistry, I guess.
Actually, the album is a complex molecule. So maybe the outer side of the molecule is the free negative, positive that will be replaced by the copper.
Yeah.
So you need to do some of the detailed study of the molecular configuration of the albumin, which is the outer chain of the molecule. And if you find it any kind of, then can it explain.
People have done that.
Yeah.
I'll tell you something very interesting. N-terminus is one of the major binding sites for albumin. N-terminus, there are 4 amino acids. I don't remember right now, but one of them specifically binds to albumin. And what is very interesting, people have done this, biologists have done this. I'm told the dogs, the N-terminus of albumin does not have that amino acid. And there it does not bind albumin. Right? So people have done all this kind of studies, right? But molecular level, why does it happen? They have pinpointed to a particular amino acid, for instance. Right?
It's a very complex structure,
Yeah.
the albumin is.
Yeah.
To find out the specifics.
Question. I work on artificial pancreas, where you're trying to do real-time control of glucose.
Yeah.
So I am interested in every minute or every 5-minute measurement of glucose.
Yeah.
So this is great for monitoring, general status.
Yes.
But if you're trying to regulate blood glucose in real time, you need
You need what is called CGM, continuous glucose
and
monitoring.
Those are,
Yeah.
we just have something on the market which is calibration free, claimed to be calibration
Just
free.
introduced very
Yeah,
recently.
from-
Yes.
from, England.
Yes.
But I still, they are, the previous generation had to be calibrated using finger pricks, which are still plus or minus 30% off the real values. So there still is a need for a good quality sensor. And again, the current CGMs are consumption. They use
Yeah.
chemicals, and so they have to be replaced every week, 10 days.
Yeah.
So
We
if you-
have plans to start working on CGM. We haven't begun that yet. Actually, just 3-4 months ago, there was a very good paper in Nature on CGM. They claim, again, this is still at the research phase, that they don't need a calibration. This was supposed to be a flexible, CGM system. I can send you that link, right? There is certainly a lot of interesting work that is happening. We have not yet started working on it. Yeah.
Okay.
But that is certainly one of the things that we would like to explore.
And that's right now what is holding back real deployment
Yeah.
outside of a lab.
Yeah. Right.
Reliability and sensing.
Correct.
In the first part of your talk, you mentioned that you had come up with a CVD reactor, which was
Yes.
then commercialized.
Yes.
Does that CVD, do you also have a CVD and TMD reactor?
For TMDs?
Right.
Yes.
Same company? Yeah?
Yes. No,
And-
that they still have not brought it out as a commercial product. But this technology has been developed in the center. One of my colleague, Vasu, you have met him, right? But that needs to be transferred to this company.
So is this like a self-contained unit which has sensors outside, so in case any of those poisonous gases
Yes, yes.
were to leak, it'll shut everything
Exactly,
off. Fully
exactly,
self-contained.
exactly,
And what
exactly.
price are we looking at on this?
I don't have the numbers at the top of my head.
Approximately.
I really don't know,
Okay.
but I can let you know that.
Sure.
Yeah.
Now, one question about the electrochemical sensors.
Yes.
You still have to add some tag like copper, right?
Not at the field. That is done in the factory. The
So-
field is from prick to result.
Okay.
They don't do anything.
So you have unattached copper ions in the.
It's a copper salt sitting
Yeah.
on a membrane.
So they
The
can
membrane
also-
is already attached.
Okay.
It is part of the strip. It's all part of the strip.
Okay.
All they have to do is take out the strip from the vial, put it to the, I have a video, I can show that to you. Put it to the device and just put a drop of the blood. That's it.
What about
No
unattached,
simple process.
The copper ions that are not attached, interfering with the electrochemical measurement,
No, there is
giving the
no.
Faraday current.
No, see what happens is
Okay.
that we are actually looking at copper which is not attached.
Okay.
That is the whole point.
Okay.
Right?
It's free
Which is
molecule.
attached is not coming to us anyway.
Okay.
It's a
Right.
free molecule.
So what?
free.
Exactly, copper is free. It is
It's
coming,
free.
and we actually want it.
Got it.
Yes, yes.
It's just your reverse calculation too.
Exactly. Yes.
Good.
And it works extremely well. It works extremely well. Yeah. And the strip doesn't need to be, stored in a specific ambient. These are very robust salts.
So copper salt you put in the blood.
No.
Not in the blood.
It's not in the blood. See, for the user,
It's in the strip.
it's already in the
It's
strip.
Yeah, okay.
It's already in the strip. For the user, it's just a prick to the result, just like a glucometer.
Glucometer.
Yeah.
So you know the actual concentration of the copper in the strip.
Oh yeah. All that is that is where the IP is.
So you also need to know exactly amount of the blood drop you're putting in.
In fact,
Yeah.
unlike glucometer, there's a very good point that you have brought in. We actually supply as a consumable, not just a strip. With each strip comes a capillary.
Oh.
It's actually a capillary dropper,
Okay.
both in one.
So it's controlled.
It's an integrated capillary dropper. For instance, for the albumin sensing, the capillary is metered to draw 30 microliter.
Okay.
Right. So you draw that and then you drop it. And, right. Yeah.
So it's a really impressive work and the center you've set up. So you have, just to understand, you have 15 faculty, you've got you mentioned
150 PhD students. Yeah.
and 91 staff.
We don't have undergraduate program. As you know, IIC, we don't have undergraduate
Right.
program.
Mhm.
It's only a graduate school.
Right.
Right. So large number of PhD students,
But you have
Our teaching load is very little, so, yeah.
You have 15 faculty whose decadal home is your center,
Huh.
and 91 staff whose decadal home is your center again.
Yes,
Right?
yes.
And
The technical staff is not paid by university, by the way.
by who?
We pay them, we bring in funds from various
So
federal
the
funding
technical staff,
agencies.
The 91 staff are on soft dollars.
Yes,
And
we
the
have
hard
to,
dollars for
that's
the-
a big headache for us,
So you don't have any hard funding for the technical staff? I see. So you have hard dollars for your equipment capabilities and the faculty. Is
Yes,
that correct?
yes.
Everything else is soft.
Yeah. Actually, only faculty. See, only faculty. Even the equipment,
It's there.
it's not that institute, like a university is giving funds for you to buy equipment. We, as a group of faculty, again, just like NSF, we have other funding agency, right? We bid for various projects. Equipment are part of that project.
For the building, for
Right.
example, when you started.
Building was given by the institute, yes.
Building was given by the.
Building was given by the institute, yes.
Makes a huge difference. If you have
It
a
does,
building.
it does, it
So in
does.
Oak Ridge, we have the world's largest supercomputer again. They just got, right? The reason they got it is, and Oak Ridge has this history, Oak Ridge National Library, we work for, Thomas was there as well. The point is, you build the building first.
That's very important.
It
That
makes
was a
huge
rallying
difference
point
if
for
you got
us.
the building there
You know,
already,
Absolutely, that was a rallying point, right?
to get the large funding for the nano fabrication center. Yeah.
Yeah.
Very nice.
Right.
Any other questions? So we should thank the speaker once again. All right.
Thank